It is also past time in terms of the semester. It is quickly wrapping up and coming to an end, and like every semester, but particularly this class, every year this semester, just not enough time to get it all in, but I just got to keep reminding myself that's okay. It's part of a whole 4-year or 5 or 6 or 7-year process to graduation. So we don't have to learn everything in one semester, but there's just always so much and so many interesting things to cover. So here's the game plan. As I think you know, we've got one more week of instruction next week and then finals week. And so to lay out where we are here, we're going to do what we can here in chapter 33. The good news about it is there's no new piece of physics again. So just like the last chapter where we learned about inductors, in other words, we took Faraday's law and we applied that to well, I guess a solenoid in a circuit, and we learned some interesting things about the properties. Likewise, this chapter, there is not another law or any more information of physics, but it is another interesting step in applying this knowledge into our circuitry. And so you'll see that if you haven't already read ahead, but I'm sure you're not behind or overwhelmed, and I'm sure you read this chapter before you came in for the lecture, as you know, this is the ideal world to be in. And so that's what I want to talk about. So there's really 9 sections. They're very short sections. They flow together. So I'll try to, throughout today's lecture, kind of tie it in. It's okay, though this is section 1, this is section 2, this is section 3. And they're really kind of short pieces all fitting together. Simply put is, we're going to just kind of go through the chapter piece by piece. They fit naturally. We're going to stop a little short because there is a section 9. So we won't do a section 9, and I thought I'd point that out. And in addition to that, then on Tuesday, that's what I've only got planned here 4 sections, 1, 2, 3, and then jumping over to 7. There's one more piece of physics we need to make sure we cover. It's called displacement current before we kind of finish up. And so it's a fairly straightforward one to finish up, and that's then the end of the lecture. Then the next Thursday, a week from today, is a test. 5 days after that is the final exam. Okay, so in addition to our regular class time, don't forget that you've got the Friday MCs. You got an additional MC. Don wanted me to point it out. He wrote it here on the board here, that he thought he would go ahead and do this on Saturday. He debated between trying to do it all on Tuesday or on Saturday, and came up with this plan that if he was afraid a lot of people may not be able to fit in on Tuesday and it would be a busy part of the week. So he goes, why don't I do the review? And so he's planning to do the review on Saturday in here, 1 to 4, and he'll cover these chapters 31, 32, and what we'll do today, 33. And then on Tuesday afternoon, and this room is full. That's part of the reason why we got to go to the smaller room, 116. And he says from 3 to 4, then he'll work whatever you guys have questions on or want to deal with from chapter 34, which is the stuff we'll talk about Tuesday morning there. And so broke the review down into 2 pieces, Saturday and Tuesday. So make a note of that. And I wanted to point that out before I pulled this down and covered it. All right. And so again, lecture today, lecture Tuesday, test Thursday, final exam Tuesday, review Saturday, review Tuesday, normal MC both Fridays. 3 to 4, I think. Yeah, 3 to 4 in the lab without the computers, not the one you guys are using this semester, but the one you might have had in Physics 102. All right, so what is this chapter? As I said, the good part about this chapter is it's no new piece of physics, but it is looking at some of the pieces of physics. And I'll start with then taking you back to generators. So one of the first things I thought I would pull up here is, do you remember this? I guess it was 2 chapters ago. What is the EMF produced if you had a magnetic field, a wire spinning in a magnetic field? Well, shall we work it off real quick? But that's why the title is called Alternating Circuits. AC, right? The voltage will change. We did this, if you remember, a couple of chapters ago here. We said the EMF produced by a generator, that is, a simple wire in a constant magnetic field, would be equal to what? And so here's N, the number of turns in the wire. This little model we have really only shows one wire. You might remember the one I passed out in class had many wires. So let's call that N. Then if we take the derivative of the flux, well, if we think about the flux going through here, if this is a uniform magnetic field, and A is the area of that rectangle that's made up of that wire, then the flux is B times A times the cosine of some angle theta. Now that angle theta is the angle between B and A. So in this position, B is going that way, A is going this way. That would be 90 degrees. Makes sense. There's no flux going through that little rectangle. In this position would be the maximum flux. Over here would be some combination of maybe cosine of 45 degrees. But the real key was taking the derivative, because as this thing spins, the magnetic field doesn't change, the area doesn't change. When you take the derivative of cosine, you get sine, but more importantly is you get the derivative of how the theta changes with time. That, if we go back to our mechanics, is the angular speed. And so if I replace theta with omega t, we were left with a voltage that looked something like this, a sinusoidal pattern. All right? And I hope I didn't waste too much valuable time here today by running through that again, but I thought it would be worth reminding you of this was 31, this was Faraday's law, this is how we generate electricity, this is what we would, call our generator or turbine. We would spin it in a lot of different ways. Sometimes you can spin it by having water run through it, but behind a dam, so it's a hydroelectric plant. Sometimes we just burn a fossil fuel and then that makes steam, and the pressure from the steam spins it. Sometimes we put up a propeller, if you will, and the wind blows and turns. So there's a lot of ways of getting it to turn, but the bottom line is you get that thing to turn and you get an alternating voltage. And that's where I want to start with. I want you to take in your mind and imagine this giant generator. This one's not very big, but some of these are giant. They're in, say, Hoover Dam right now, 300 miles away. The water's running through, it's spinning, it creates a voltage. There's wires then connecting from Hoover Dam all the way to here. And so the first step here is to look at what is coming out of our wall. Because what comes out of our wall, as I mentioned, is an alternating current, an AC current. And so the first time, at least in this class, I know some of you guys in circuits have been doing this already, but for the most of you, for the first time, let's look at circuits where we don't have a constant voltage source, but it changes. And what's nice about that is that's a lot of the world around us. That's why we need to take a moment to study it. So when I look at the voltage coming out of this plug, I would ask myself, well, what is that voltage? So let's give it a try here. The reason I brought this oscilloscope out here was to show you, let's just clear some of the measurements on here, and let's turn off channel 2, and to show you this. So here I have a little probe. The probe is here so that I can plug it in and take a look at the voltage. Now I guess my plug is over here on the side, so you may not be able to see it, but here's what I'm going to do. I'm going to take this little hook and I'm going to grab onto that plug. And that way, when I plug it in, I can ask myself, what is the voltage that I'm getting? And so the oscilloscope should measure the voltage. And that's my point. My point is to prove by using the scope that what we have is a voltage that is generated by this spinning generator here. Now, let's take a look at some of these numbers. Notice, these are pretty big. How many volts per division? This is 50 volts. And so if you don't already know this, you need to know that the wall plug is written in this form. The voltage coming from it looks like this. The voltage, what the heck happened to that one? The voltage coming out of the wall, and maybe I'll just put V as a function of time, is some maximum voltage times sine omega t. And of course, that makes sense because this is how it was generated, Faraday's law. So let's fill this in. What is this maximum voltage? What is this frequency? Yeah, again, if you don't know, you need to know to do this chapter here. The frequency, let's see if I can make a quick measurement here. Where is frequency? And there's a frequency. How fast does this thing spin around? How many times a second does it go around? 60, right? And so this is 60 hertz. 3,600 RPMs is how it is built here in the North America grid. And I guess we're in the western part of our grid here. And so this is 60, or putting the math together, 2 pi times 60 is about 377 times the time. All right, so that's the rate at which the voltage is changing. How high does it go up? Well, 50, 100, 150. Looks like it's going up to about 170, 175. Well, again, maybe I'll make a measurement here. There is maximum on here. Maximum, I'll even do minimum, why not? But it shoots up to about 170, 71, 72, shoots down about the same amount here. This one's needs a little adjusting. It's not exactly centered, but let's call it 100 and, I don't know, 72, 73, 74. Truth be told, it kind of varies slightly depending on how many other people are plugged in and operating things here. But that's what I wanted you to see. And I certainly didn't want you to confuse it with the 120 volts. What we're going to call here in a few moments 120 RMS is a little bit different than here what I'm talking about, the peak voltage. But there is one good example of a voltage that changes, and why we want to spend time this chapter studying what would happen if you hook things up to a circuit where the voltage was changing. So now that we see that, let's go ahead and ask this question. What if I take all these pieces and all these elements that I have been learning for these last couple of weeks, like resistors, capacitors, and inductors, and I put them in a circuit where the voltage is changing? Not just a constant DC voltage. We've done a lot of that. But the next step is, what if I put it in a circuit that's changing? So let me introduce you to what might be a new symbol for you. This then is going to be the symbol I am going to use when I want to talk about an AC signal, a sinusoidal voltage, a voltage that goes up, down, up, down, up, down. In other words, the voltage as a function of time would be some maximum voltage times sine omega t. So let's just take that and hook it to a resistor. We did resistors first. They're the easiest ones to work with. You're going to see that here too. Resistors are by far the easiest ones to work with. So let's hook it up. Now, truth be told, since I don't want to be playing with such a high voltage, let me disconnect my probe here and change things a little bit. I'll put the probe over here, and I'm going to take this, which is again a signal generator. We've used it a lot in the lab. I'll set a frequency somewhere around 1,000, and so this is making a voltage that will be going up and down 1,000 times a second. And maybe I will start off by just showing it. There is the signal coming from my signal generator. Now let me point out a little subtlety here. Did you notice I only hooked up one wire? Why? Right here. And so keep in mind that this signal generator is plugged into the wall there. And it has 3 plugs. And one of those plugs is a big fat one, which we call a ground. Now the reason I say that is because I have over here my scope. And that too is plugged in. And that too has 3 prongs on it. And one of those is a big fat one. And coming out of my scope is what we would call the signal red, and the ground, which we would call black. And what you may not know is that those are hooked together. Although many of you do, because we talked about this in lab. But for the last of you who haven't done the lab today, that is actually hooked together. Likewise, the same thing happens in the signal generator. So I don't really need to hook the 2 black ones together. They are already hooked together. So that could be a blessing or a curse, depending on what I'm trying to do. If I'm just trying to hook things up, I could take advantage of it. And I am in this case. So I would call it a blessing that they're hooked together. But other times you may not want them hooked together, and hence then I would call it a curse. And then there's things we can do to get around it. But that's not necessary for today. I just want to say that I took one wire and I hooked it right there, right? And so that is my voltage. But here's my question for you. Going way back, before we did inductors and capacitors and before things got a little harder, we just had resistors, right? Let me ask you this. If I were to make a circuit out of this, and so here's my circuit. Let me disconnect the scope for a moment. So I'll come back over here and say, okay, I don't need the scope here, but let me hook up a circuit. And in this case, I'm going to take the circuit. Here it is. I've got this signal. I'm going to send it to a resistor. So you might remember this one from class. Here's my resistor box. I'll set it at 1,000 ohms and say, all right, I am going to send the signal in to a resistor and then back. And so what I have in front of you is hopefully matching this picture. And if I were then hooking up a wire to my scope, I could then see what is the voltage coming from here. All right, so let me take a wire. Let me take that channel 1. Let me get a longer wire. Let me take that channel 1. Let me hook it right there. All right, and so channel 1 is telling me what is the voltage going to that resistor. Fair enough? Now, what current do I get? Well, let's run through the math. As I said, there won't be any new physics here, but we do know this. We do know that the sum of the voltage around a loop is 0. So, if I write off right off Kirchhoff loop rule, I would say this would be the equation. I mean, the only thing different between what I'm doing now and what we did back in chapter 27 is that my voltage changes with time. And there's going to be some interesting consequences of that. Not for the resistor, though. They're kind of boring. But it sets the groundwork for what is about to happen with our inductor and our capacitor. So if I follow this logic through and replace this, this would be V maximum times the sine of omega t minus IR. After a couple of steps in math, I will get the equation for the current. The current would be the maximum voltage divided by the resistance times sine omega t. Fair enough? And so look carefully at this equation. Probably not a surprise. I'm hoping it's not a surprise. What is this equation saying? Well, number one, it is saying that the current changes with time. Well, okay, not a surprise. The voltage changes with time. So we go from a DC to an AC. The voltage changes with time, so the current changes with time. Look how it changes with time. It changes at the same frequency as the voltage. Not a surprise, it's the voltage that's making the current. Okay, look at the magnitude of the current. Oh, it's the magnitude of the voltage divided by the resistance. So really, isn't this just Ohm's law with the time stuff on here? Yeah, not a surprise, right? Exactly. That's exactly what would happen here. In fact, to prove this to you, let's then also look at the current. And so I am going to take channel 2. So I'm going to take the red one from channel 2 and hook it to get the current. Now here I'm going to have to play a little bit of an experimental technique. Scopes only measure voltage. So what I'll do is put a small little resistor in there and say, okay, I'm going to put this small little resistor in there, and technically it's going to measure the voltage, but that's got to be proportional to the current there. And if that resistor is small enough, we would argue that it hasn't really changed anything. So I'm going to put a small resistor, like 1 ohm there, and go, okay, what happens there? And actually 1's a little too small, so I'm going to set my dial at about 10 here. And so here is my second one. Let me set it at a real small value and kind of sneak it into my circuit. So this is like not really there. All right, so I'll put it in the back like it's not really there. I'll disconnect channel 1 here and say, okay, here's what's happening. It's going from my signal generator to my first resistor, the real one I want. Then I'll send it to the second one. The second one is kind of this fictitious one that's so small that it doesn't really affect it. But what it does allow is it allows me to then look at both the current and the voltage. So here is channel 1. Here's the voltage, so that's going right to that first resistor. And then this one is channel 2. Let me turn on channel 2. And what do you see on channel 2? Don't you see it changing? The current is changing. What frequency? It's the same as the voltage one, which it looks like I'm set at about 793 hertz, right? And of course, it has a certain value that is not the same as the voltage on the, if I'm saying this right, it's not the same as the voltage, but it is the voltage divided by the resistance. And watch what happens if I change the frequency a little bit. I'll come over here to my signal generator and I'll increase the frequency. Well, if I increase the frequency of the voltage, I increase the frequency of the current. That's not a surprise. But notice that the amount of current didn't change, right? Because again, isn't this saying this is the amount of current? The amount of current depends not in any way on the frequency. It just depends upon the value of the resistor, right? And so I would only change the value of the current if I change the value of either the voltage or the resistor. Fair enough? All right. And that's probably the simplest one. And so I have a little graph there. I have a little chart, if you will. I have what you might call two sine functions. Well, let me turn this off for a second and go back to the computer. Let me open this chapter 33 and give you kind of, I don't know if math lesson is the right word, because my colleagues in the math department would probably shoot me if they heard that. So I don't want anybody to say I'm teaching you any math. Okay. But there is a really nice way of looking at trig functions through a process called phasors. And if you haven't heard that word before, which I'm suspecting many of you haven't, let's take a quick look at it. What I had on the board a moment ago was this graph, right? Two sinusoidal functions. Okay? But if I take you all the way back to your trig class, where did these come from? Why did we even have sine functions? Do you remember? Remember where they came from? Do you remember doing a unit circle in your trig class? I mean, the whole point back in your trig class and the whole discussion about sine functions probably has been so long ago, you might have forgotten just the basic idea of a sine function, and it is simply this, that if I take a unit circle, meaning a circle of radius 1, and if I were to draw a line out to here, how could I graphically represent the sine of this angle? Isn't it how tall it is right there? Right? And the cosine would be represented by how far it's out here, right? Now, I don't want to go down that road. I just want to focus on the sine function. And so, if you make a plot here, and I remember my trig class, the teacher came in with a little circle and a string and goes, okay, let me hook the string right here. And he just continued to wrap the string around here. And as we wrapped the string, the length here, the angle was plotted here. And then as we wrapped it around, we kept measuring the height. And it went up to here, and then it got to some maximum when we got to a distance of pi over 2 for the length of the string. And then as the string went further, the height went down until you got all the way over to here, where the length of the string was pi. Any of this look familiar? Because one way of looking at sine functions are like this. Like this. Ways that you are probably most familiar with. But another way of looking at sine functions, which can be very useful at times, and it will in this chapter and in other chapters next semester, is to think of this as a stick that is spinning, like the length of a string. And so my phasor is this, and it spins. If I hold it this way, the sine function is the size of that shadow. And if I spin it, the size of the shadow changes. And maybe a better visual picture is an animation we put together that, I can call it up here real quick. It's on our flash page. It's down here in the optics, phasors, is this. There's two ways of looking at a sine function. This is probably the way you're most familiar with, a sinusoidal pattern. But a second and extremely useful, which we call phasors, is to think about it as a stick in motion. And that's why they're hard to draw on the board or hard to describe to students in a textbook, because it's a stick that's spinning and your textbook doesn't have spinning pictures. So the animation here is much nicer. Of course, you'll see it in your in your book like this. They'll say, okay, here's a spinning stick. But notice this is the vertical height of it. And in the animation, we just put the vertical height there so that you can see what's going on here. So my question for you as we get started here with phasors is, as this stick spins, do you see how if you take the vertical height, that's this, put it over here and put it on a conveyor belt, do you see how the vertical height projected onto here is the same as a spinning stick over here? And if you get that mental picture in your mind, phasors actually become extremely easy. And they got some nice little properties here. And so if you just let it play out, my question for you is, do you see this and this as the same thing? And so that's what a phasor is. It's a spinning stick. It's a way of looking at a sine function not as a curve in space, but as a rotating arrowhead. This one. Okay. And so there is your phasor. Now, the reason I say that is because if I come back to this description and say, all right, if I made a plot of voltage and current versus time, what would the voltage look like? Well, I guess the voltage would look like this, right? What would the current look like? I'll go blue for current. That's what we had a few moments ago. How would I do it now that I have a phasor? How would I represent these same two sine functions with two phasors? One phasor for each sine function? Well, I would have one stick, which represents the voltage, and a shorter stick in phase, representing the current. Spinning. And again, it's hard to show that spinning. That's why I like this. The black one is the voltage. The white one is the current. As time goes along, that looks like that. In your lab manual, your author, lab manual, in your lab book or textbook, your author says, here's that graph. Now it looks like he made his current bigger than his voltage. So that's only possible if R is less than 1. But it certainly is possible. So maybe I shouldn't have done that. I just noticed that I made my volt. I usually think of resistance being more than 1. So the magnitude of the current is a smaller number than the magnitude of the voltage. But it doesn't have to be. It depends what R is. But the point is, he's trying to illustrate in here that picture this spinning. And as I said, for many of you, I am sure this is your first exposure to what is a phasor. But as I hope you'll see, it can become really, really powerful. Why? Let's watch this for a moment. Not very useful here. But let's go back to that little animation on phasors. Let's put a second sine function up here. Now this is more complicated than we have so far. This is a second sine function that is out of phase. And so again, you're probably more used to looking at sine functions like this, a green and a blue one, where they peak at a different phase. Fair enough? But how would those look in a phasor diagram? Well, they'd just be two spinning sticks, right? In this case, a green one and a blue one. The green one's a little bit longer than the blue one. The one I did up here is kind of boring because they are in phase. But this one is where you begin to see the power of the phasors, is they are out of phase. This one has something that looks like this, right? Where the blue one is at a phase phi before the green one. Did I say that right? Yeah, so as it scrolls across here, the blue one peaks before. That's a terrible time axis because it's going to be the reverse of this. But there is our phasors. Okay, now again, maybe that's not too big of a deal. That's just two sine functions. But here's the real power. Add them together.
How do you define which one's first and which one's last?
Well, in this case, I'm just saying there's going to be one first, one second. Okay. In a moment, we'll go through the physics and go, okay, well, this one has to be first and this one has to be second. So, but I guess in this picture, I would say the blue one is first in terms of it swinging around. It reaches a peak first before the green one, I guess is what I mean in that one.
I meant you could say that the blue one is, I don't know, 60 degrees ahead, or you could say it's 300 degrees behind.
Sure. You're right. And it's the same thing, so.
How do you define?
Yeah. Mathematically, that's the same. But, well, as you'll see here in a second, we can't have angles more than 90 degrees for what we're about to do. So we would just say the 300 is not going to fit our physical picture. Mathematically, it's the same. Well, anyways, here's the real point. And hopefully over the next hour, these phasors will sink in at least somewhat. Because the goal here is not really to get you an expert in phasors, but get you prepared for classes in the future where you'll be looking at this. Because what if I were to ask you to add two trig functions together? Add the blue one and the green one together. How do you do that? It would be a little tough with this one. You would have to do a bunch of trig identities, right? How about this one? This one's a piece of cake. Add those two together, and it just comes geometry. You add two sticks together, two vectors together. You know, come on, you know how to add two vectors together, right? And the addition of those is the red one. And so instead of doing a trig problem in terms of trig identities, we break it down into a vector problem, and we just have to add the magnitudes of it. So blue one and the green one actually become a geometric question, not a trigonometric question. And so that red one is my total result of those two sine functions. Keep that in mind. Again, don't expect you to digest all that in the first setting. But before today's over, we'll do this 2, 3, 4 times. And hopefully it'll begin to sink in. And so that's our phasor. Now, so far, then this is much more complicated than what we have. We just have a very simple sinusoidal resulting in sinusoidal current. Let's change it though. Let's get away from the resistor. What if I replace this with an inductor? How would this change if instead of having the resistor here, I had an inductor? Okay, now I'm going to have to clear the board here, but keep the resistor in mind, because we'll come back and compare everything to how does it behave compared to the resistor. All right, well, again, as I said, no new physics here, but let's run through the math. I guess the first thing I would say is, okay, here's the sinusoidal function, right? Add up the voltage around a loop, I should get 0. Okay, so I should get voltage as a function of time minus, maybe I'll just go back to the last chapter. How do I get the voltage on an inductor? L di dt, and that has to equal 0. Fair enough? Now the voltage, it follows this function, V maximum times sine omega t minus L di dt. Now my question for you is, could you solve this for current? I mean, if we have a voltage that keeps changing with time, so I'll switch it back, right? And so I will go back to this setting. I will turn off channel 2. So there's looking at my voltage. I'm not going to change that. But in place of this resistor, I am going to put this inductor. Maybe I'll change the frequency a little bit so it looks a little nicer up there. But for those of you who didn't see this in the lab yet, because your lab's today, this is my giant inductor, if you will. It's got 500 coiled, or turns in here, as it says, 500, and you can kind of even see the copper wiring in there. So I will disconnect my resistor, and I will connect my inductor. And so I should have the voltage. So there is the voltage. There's the sinusoidal voltage. My question for you is, what does the current become? Is there anything stopping the current from flowing? What? I mean, why doesn't the current just be infinite amount? I mean, would there be anything opposing the current from flowing? Yes, what is it? Yeah, it's Faraday's law here, right? And so, remember what we said is that when this object, the voltage, is trying to shove current through the inductor, during that moment in time, there would be an induced EMF. And so, I want you to see here that this is not just going to be an infinite amount of current. There is an opposition to the current flowing. It's not the resistance. And so remember, this little resistor down here, you want to pretend like this one doesn't exist. This is small. This is only in here for the measurement. And I know that all wires have a resistor, but that is small compared to what I want you to see is this inductor is opposing the current from coming in. Notice I didn't say resist it, because it's not resistance, but it is an opposition. There is something stopping it, and that's Faraday's law. And so as this thing changes, this creates an EMF. In fact, Faraday's law said the EMF is proportional to the rate of change. So what would I expect with high frequencies here? I would expect this to have significant opposition to the current at high frequencies. And as consequences of that, at high frequencies, I would expect very little current. But what about low frequencies? Very little opposition, because Faraday's law says the back EMF is proportional to the rate of change. So at low frequencies, I would not expect to get much of a back EMF, and therefore a lot of current, not much opposition. And here's what's neat. One of two things I want you to see about this inductor is the amount of current is now going to be highly dependent on what frequency we're on. High frequencies will really oppose the current. Low frequencies will not. All right? Let's see it in the math. Can you solve this for current? Well, I'll just put the derivative of the current on this side, and over here get the maximum voltage divided by L times sine omega t. And of course, to solve for current, I got to do an integral. So I will take my integral. On this side of the equation, I get current. What do I get on the other side of the equation? All right, so I'll leave the Vmax and L alone, or pull them out in front. What is the integral of a sine? Cosine or negative? Must be negative. Negative. Cosine. Omega t. What? Over omega. Good. All right. Now, look carefully at this. What is this math saying about the current going through an inductor in an AC circuit? Well, first of all, the current changes with time. Okay, not a surprise. Second, it changes at the same frequency as our voltage. Okay, not a surprise. But what might be a surprise are two other interesting effects here. Look at this right here. Doesn't the amount of current depend on what? The frequency. We didn't have that with the resistor, right? With the resistor, we just had V divided by R. So you would probably expect a V divided by L. That's not a surprise that the amount of current depends on how big that inductor is. But what is added to this is the amount of current depends on what frequency we're at. Now, hopefully, now that we did the math and I explained the concept earlier, hopefully that's not a surprise, because again, I'll come back to the concept. Doesn't the opposition to the current caused by Faraday's law, and doesn't Faraday's law say the back EMF is proportional to the rate of change? So if I had a very large rate of change, if I had a very large frequency, I would expect very little current. Then on the other hand, if I had a very small frequency, I would expect a lot of current. And so we already mentioned that one, but do you see the second one here? The current does not peak at the same time as the voltage. Let's draw a graph here. If I were to draw the graph of the voltage, the sine function looks something like that. What does the current function look like? So maybe I should put voltage. What does the current look like? Right. I mean, it's a different size based on this number, so I'll draw it a little smaller in amplitude. Maybe, so this number is greater than 1. But the neat thing here is it's a negative cosine function. So what does a negative cosine function look like? Now I guess it starts down here and does that, and then peaks here, and then comes down and then has a negative peak here. And so this is the current as a function of time. So I'll say it again in case you missed this. There's really two things I want you to notice. A, the amount of current you get depends on the frequency. B, the current actually is behind or lags the voltage. Now maybe that's not a surprise, because if we go back to Faraday's law, when do you get voltage from Faraday's law? When you're trying to change the flux. It's not when you have the current, it's when you're trying to put the current in. So as you try to put the current in, that's what's happening right here. At the very beginning, you're trying to shove the current into the inductor. It's not there yet. You don't have the current yet. It's going to take a little while later before you get the current. And so what ends up happening is something like I guess here, you're trying to change the current by a lot and you get a lot of voltage. It's later on, you get up here to where the current has reached its peak and is tapering off, is where you're not changing the current. You don't expect it to get an EMF. And so the EMF and the current are what we call out of phase. By how much? 90 degrees, right? Plus 90, minus 90. We'll talk about that in a second. But see how they differ by 90? Which one comes first? Voltage or current? Doesn't the voltage come first? And I'll give you two ways to remember it. One is just the physics. This is Faraday's law. You got to get the voltage first because you are trying to shove the current in, and you're going to get voltage first. Then later on, you'll get the current. Fair enough? Or one of my favorite little tricks is I like to call inductors Eli. And in a minute before we're done, we'll learn about a little character called Eli the Iceman, a very popular book of kids' electronics that gets Eli. Now look closely at Eli. Look how it's spelled. EMF before current in the inductor. E before I in the L. Did you catch that? E, L, and I. No, you didn't catch it. Try it again, right? Inductor. L for inductor. Which comes first? The E or the I? The EMF. So EMF comes before the current. If you can just remember Eli. Personally, I like just Faraday's law. I mean, what else could it be? It's Faraday's law, right? But in case you can't remember Faraday's law, you're in trouble. But if you can't remember Faraday's law, can you remember Eli? Right.
So when time equals 0, we have the y-axis there. Wouldn't the current start right after you have some voltage at time equals 0?
Well, at time equals to 0, it's probably not well represented in this graph because this is a whole continuous function. So there were things going on before time equals to 0.
That's what I was getting at.
Yeah.
But if that y-axis was time equals 0, then they would both start right there, right?
Yeah, so what there would be is a transition because I would have a combination of an AC circuit and a what you might call in math a step function. I'm hooking it up. I'm going from nothing to something. And so there's two changes. There's the change of going from something or from nothing to something. That's a transient part of the solution for those of you who've gone to your math 220. And I'm not completely ignoring the connecting part. So this is after you connected it. This is, you know, a couple microseconds after you've connected it and things are stable. Now, to convince you, let's hook up the experiment here. I have already been looking at the voltage. Let's look up the current. If you remember, the current is on channel 2. So if I click on channel 2, ta-da! Are they in phase? No! Which one peaks first? The voltage. And so as we scan across, we get voltage first, E, before we get I. And so we've got our Eli there, right? And that's what I wanted you to see here. They are not in phase. One is a sine function and the other is a negative cosine function. And that's the physics behind it. Again, no new physics, but obviously just applying AC circuits, Kirchhoff's law, and some mathematics. And that, of course, the inductor, the mathematics came from Faraday's law. So between conservation of energy, conservation of charge, and Faraday's law, that's what popped out of it. And the other thing I wanted you to see is not only are they not in phase, and of course the voltage is ahead of the current, or the current is behind the voltage, whichever way you want to keep it in your mind, is the interesting thing on inductors and why they become useful in your circuits class. And it's too bad we're going to end the semester. We could really do some fun electronics now here, but I guess that's what your circuits class is for. All right, so later on, or some of you are there now, some of you now, some of you later on, you're going to play with these inductors. And notice the second thing here says that the amount of current depends upon what frequency I'm at. Remember I said the high frequencies? What does this say about the high frequencies? You're going to get very little current. So inductors are great for blocking high frequencies. If you have frequencies you don't want, you put an inductor in line with it, and it stops all those high frequencies. It's a high frequency filter, blocks all those things. And watch this. If I take the dial and I turn up the frequency, watch what happens to the magnitude of the current. Can you see it going down? Yes? No? Didn't the current go down? And what happens if I decrease the frequency? See that current go up? And so the amount of current is very dependent on the frequency. And we didn't have that for the resistor. The resistor was boring. And because of that, not really as useful or creative in building things. It's because it always just does the same thing. The resistor's in phase and the current's just voltage divided by resistance. It's nice in this sense. If you got to study it or do a homework problem or a test problem on it, that's nice. But it's less interesting because it doesn't change the amount of current based on frequency. And it doesn't shift the phase between the voltage and the current. And so that inductor will. So, over here on the side, when I had my resistor, I had a current maximum that was equal to the maximum divided by the resistance. What do we see now with the inductor? Well, this is its maximum. And if you look closely at that, I think you will see that it looks like, if you will, Ohm's law, doesn't it? Doesn't it have some number, voltage, divided by something? And so our maximum voltage is the frequency times the inductor. We like to call this X sub L. This is the reactance of our inductor. Yeah, I guess I'll just put it reactance. Probably best put as an inductive reactance. Again, notice I didn't say resistance. It's not a resistance. But does it have that same basic effect? Is it opposing the current? Yes. Now it's opposing it because of Faraday's law, meaning there's an EMF produced because of the change in flux. And so what we will write then is we will write it so that it looks like Ohm's law as X over L. And so that's how much current we will get. And of course, notice it depends upon the frequency. And so maybe I should put X over L is equal to omega L. And this, as you can now see, means that this number gets big when the frequency gets big. Large frequencies mean very little current going through our inductor. Our inductors are what we often call high frequency blocks, or DC or low frequency passes. They let the low frequencies in. They block the high frequencies. Yeah.
In circuits, we're using impedance. What's the difference?
Ooh.
I know you have the imaginary part.
Well, I'll give you the short answer now and we'll get it in a couple of minutes. But when you put all the opposition together, resistance, reactance of the inductor, and reactance of the capacitor, when you put it all together collectively, you call it impedance. So it's not much different. It's just the total of everything. Yeah, yeah. So at this point, I don't have, right, this point I have not used the word impedance because I haven't put everything together. But I do want you to see it is opposing the current, and it's a little different, so we don't use the word resistance, we use the word reactance. It's Faraday's law. Now, probably not a surprise, but maybe it's worth, what would this look like on a phasor diagram? What would this graph look like? So here's my grid. Yeah, it would be two spinning sticks. It was separated by 90 degrees. There it is. Now maybe get it in the same order. Which one would peek out first? I guess would be my black one. Right? And so as this spins, my question for you is this looking like that yet to you? Right? And so there is my phasor diagram. Switching back to your lab book here, not lab book, your textbook, thank you, and I look at what your author has done here in terms of the phasors for an inductor, he's got this graph. He's saying, look, you can look at it in either way. You can look at it as a voltage and then the current peaks a little later. There's your E line. EMF first, then the current. And that's what this set of sticks would be. Here's the brown stick representing the voltage. Here is the purple stick representing the current. Two of them at 90 degrees spinning. And in mine, I got my voltage bigger again. He's got his current bigger that way. And so he wants you to mentally think of this as a phasor spinning around. And again, as we're about to get to, thinking of the phasor is going to be nice when we add all these together. What if we have a resistor and an inductor together? And we've got to add these trig functions together. And it's going to be a lot easier with our phasors. Yeah.
So if you're inducing current on a secondary coil, would the current come before the voltage?
Okay, now you're asking a question different than what I'm showing, right?
Yeah.
Okay, so what I'm showing, there is no secondary. This is a self-inductance. Right. Okay, so if I had another coil next to it, then I guess what I would get is the voltage from here would go through here. I would not get current till 90 degrees later. That current then would make the flux that induces in that voltage, which is 90 degrees behind that. Yeah, so the induced voltage in the secondary is 180 degrees out of phase with the primary. Yeah. Yeah. Yeah.
When you think of the arrows as spinning, are you thinking of them as spinning in the plane?
Yeah.
As it's translating, or are you thinking...
No, this doesn't translate at all. All this does is this. In place. And as time goes. And so that spinning, if you can think mentally as the height, being representing the height at different moments in time, we don't have a time axis here. The fact that mentally it's like a video in your head.
So for a sine function, it would be like the vertical component rotating around the x axis.
Yeah. Right. So there's the vertical component. And then this is the vertical component plotted at different moments in time. And so that and that, same thing. Right? All right, so like I said, the phasors are going to become very, very useful here. But we also see something very interesting about inductors, right? Let's try capacitors. What do you think is going to happen there? All right, let's clear this off a little bit here. Let me grab my eraser. Let's ask this question. What if I change this circuit? And instead of having an inductor, I have a capacitor. And I can ask the same questions I've been asking for the resistor and for the inductor is if I hook up a capacitor, C, and apply an alternating voltage to it, what will the current be? Will there be any current? Will the current go to infinity? Well, again, when we did DC, we said, well, what's going to happen is the capacitor is going to fill. And if this was just a DC source, what would happen is you would only have a current for a small moment in time, right? And eventually the capacitor would fill, and then how much current do you have? None, right? If it was DC. But if it's AC, as you start to fill up the capacitor, you begin to build up a charge. And the reason you stop the current is because it builds up, but what if you change it? And so before the capacitor can fill up, you change it, so now you discharge. And then you charge, and then you discharge, and then you charge, and you discharge. Isn't it always having current? And interesting enough, it's kind of the opposite effect. I mean, is there going to be an opposition to the current flowing? Well, there is, but not till the capacitor builds up a charge. So in other words, if you have low frequencies, what's going to happen there? Low frequencies are going to give a chance for the capacitor to fill up. And if the capacitor fills up, it has an electric field and stops the current from coming. So low frequencies, I would expect very little current. And that's just the opposite of the inductor, right? The inductor, because of Faraday's law, I expected very little current when I had high frequencies. But for the capacitor, I expect very little current on the low frequencies. But on the high frequencies, I have really very little to almost no opposition, because until the charge actually gets a chance to build up, there's no electric field stopping the current from building up. Let's see what the math comes out.
So if you wanted to block high frequencies to a subwoofer, you would use inductors. If you wanted to block low frequencies to a tweeter, you'd use capacitors?
In series. And just the opposite if I hooked them in parallel. Because in the parallel, they would bypass it. So, I mean, it's not, so the answer is a little more complicated. Maybe I shouldn't have brought that up. But yes, how's that?
Okay.
Yes. Yeah. Yeah. And so we often say this. We often say that inductors are low frequency passes. They let the low frequencies in, as you said, the subwoofer. But the capacitor stops the low frequencies. It lets the high frequencies in. So you put that one for the tweeter. Exactly. And that's how you get your different band pass on your equalizers and how the different speakers are arranged, because they have different amounts of inductance and capacitance hooked throughout your circuitry. And then you can even, and you might as well go mid-range as long as we're talking about speakers. That mid-range, I would put an inductor and a capacitor of a certain value, so I don't get the highs and I don't get the lows. I get something that's a balance between the two, which we'll do next here in just a second here. All right. And then again, and that's only if I did them in series. I could do something else in parallel, which would have other advantages too. So I probably would actually do that. But for this class, we're only going to do series. That's all we have time for. I think in your circuits class, you're doing series and parallel stuff. All right, but let's run through this. Same idea. Again, can't overemphasize this. No new physics here. Let's write off Kirchhoff's loop rule here. And I would say, okay, voltage is a function of time. Then minus the voltage on a capacitor. Now, it's been a while since we've done the capacitor. What was the voltage on a capacitor? Q over C, right? Capacitance is charge per volt. Bring the volt over, the C over. Okay, so there is your equation. That would be your loop rule, right? The source and the capacitor around the loop, ignoring this little one we're using for measurements, okay? And then that would be the volt. Now, let's put in our equation. Let's put in the maximum voltage, sine omega t, minus Q over C equals to 0. I'll solve this for Q as a function of time. So this would be Q, the charge here on the capacitor. Bring it over, and then I would get then the maximum voltage from my source times the capacitance times the sine of omega t. All right, so there is the charge on the capacitor. What I really want to look, though, is what is the current. So next step, how do I get current? All right, I'll take the derivative. So the current as a function of time, being the derivative of the charge, would be what? Well, I guess I would have maximum. I would have C. What's the derivative of sine? Cosine with an omega. Okay? Now, let's look closely at this. And you'll see a lot of the same things that we just discussed, but in reverse. First of all, the fact that the current changes with time, not a surprise. You're putting a voltage that changes with time. The fact that the current changes at the same frequency as the voltage, not really a surprise either. But the other two surprises are interesting. Isn't this right here the maximum current? And doesn't that maximum current depend on frequency? And when the frequency is small, what does this say? current is small. And isn't that what we just said conceptually 5 or 10 minutes ago? We said if you were at a low frequency, this would make the capacitor build up the charge, and when it does, it gets an electric field. Call it Gauss's law. And so the capacitor blocks, opposes, has a reactance. It stops the current at low frequencies. But look at high frequencies. What is high frequency saying? Lots of current. And so the amount of current that goes through this circuit is dependent on what frequency you are. So just like for the inductor, but reversed. And so we can even write that over here for our capacitor. The maximum. I'll do a little bit of math though. The maximum, as you can see, are these three multiplied together. You're probably going to think I'm crazy for changing something so simple into a compound fraction. But when written in this form, doesn't it look like Ohm's law? Where we have the voltage divided by, and guess what we're going to call this? This is reactance. This is how the capacitor is opposing, it's reacting. It's a capacitor reactance. Oh, we like to call this X sub C. Then it doesn't look so bad. We just go maximum divided by X sub C. And so it has that same look and feel. We've been doing that for resistors. We've been doing it for inductors. We might as well make it look like for capacitors to kind of help our thought process that what is happening is we get the same thing here. And so this is V maximum divided by XC, where XC is 1 over omega C. Right? And so again, just like the inductor, notice the amount of current depends on the frequency. And also notice the phase here. If I was drawing a plot and I was plotting the voltage as a function of time, what does this say about the current? You don't get your maximum current at the same moment you get your maximum voltage, do you? When do you get it? Well, what does a cosine function look like? And so the current as a function of time, again, like the inductor, is not in phase, but which one's first? Current. Now, doesn't that make sense? Because when do you get voltage on your capacitor? Yeah, after you get charges on it. So you got to have the current first to build up charge into the capacitor before you're going to get a voltage. That's just the basic physics that we've been learning this semester. And again, good applications of our basic physics here. And so as you look at this one, you will see that you get current before your voltage, before your EMF. If I write that this way, I would say I get current first before my EMF in my capacitor. Ice. So Eli the Iceman is a very famous electronics book. Eli Iceman. And so it keeps the same. And it's got a little picture of this Jewish-looking cartoon guy in the snow. It's Eli the Iceman.
Is that a negative vibe too?
Negative where? Did I mess up?
I think that it should be negative, but I can't tell if you meant to do that.
Well, derivative of sine is just a cosine. So.
Because when I look at the math compared to the last one, the last one had a negative Vmax, right?
Yeah, the last one had a negative in front. The inductor had a negative in front, which is why we had a.
Positive,
So this positive.
It says equals, and then there's an underscore. I have to use.
Oh no, that's a smudge.
Okay.
That's an I with a smudge. Is that what you were?
Yeah, I was just not sure if
Yeah.
it was negative or not.
No, okay, yeah. So, all right, but again, probably don't need to spend too much time here other than to say, look, this is what it should look like. I hope. Shall we try to hook it up here? All right. So, you might recall, here we go. Here's the capacitors from lab. Here's the inductors. What if I were to replace, what if I were to replace, and I'll turn off channel 2 for a second. There's the voltage. So I will take it from my inductor and I will hook it to my capacitor. Okay, so there's the voltage. Anybody as excited as me? Channel 2. There's the channel 2. And maybe I will turn the frequency down a little bit so it will show the effect more extreme. But this one here is the current. And the current, as implied by ice, right, comes before the EMF. Okay? And so there's the I and there's the V. They're out of phase. And better still, what happens if I change the frequency? What do you think would happen if I went to lower frequencies? Did you notice anything about the current? Went down. Right? That's what the reactance of this capacitor is trying to say. That when that frequency is low, the reactance is big. It has time to build up charge. It stops the current. And so capacitors, at least in series, block those low frequencies. If I turn up the frequency, higher, 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 the current gets more and more and more and more and more. Still out of phase, but different amounts of current. So again, both the inductors and the capacitors, I want you to see that they have an opposition. They have a reactance. So we don't call it resistance, we call it reactance. Okay? But it also, in addition to having a reactant, or maybe I should say the reactance is frequency dependent. So the amount of current depends upon frequency. But in addition to that, there's a phase relationship between the two. Now I said as we went along I would mention what sections we've done, and I kind of forgot, but the first thing I did was, I guess, section 1, and then we get to the resistor in section 2, good. Then we went to the inductor in section 3, and now we just did the capacitor in section 4. I don't know if I call this the grand finale, but what if we had them all three? What's going to happen? So we'll do that next, but I need to finish. What would the phasors look like for this? Phasor, where is your inductor? No, I'm sorry, we're at the capacitor, right? That's the inductor. Don't want that one. Where is capacitor? This must be capacitor. Yay! Okay. So here's your little phasor for your capacitor. Again, making a chart. I would have one little stick in blue, and it would be ahead of, and that one's in purple there, but they've got it drawn off at this angle there. And then at 90 degrees to that, they've got the voltage. So there's the voltage as a function of time. There's the current as a function of time. They're at 90 degrees to each other, and they're spinning around. Okay? And so, again, if it helps, this is what it's trying to say, is it's spinning. Okay? And so that's your two sinusoidal functions. Now current and voltage we probably never want to add together, so just writing the two together in the same diagram is pretty simple. But now let's put all three together. Let's make what we will call an R, an L, circuit. All three of them together with a alternating voltage. What will happen then? So we've learned the individual pieces. I kind of like that. Maybe I should have left, because I'm going to still hook it up. Should have left my scope here. And now, let's hook an inductor, a capacitor, and a resistor, all in series. And I'll leave my small one off to the side, and I will look, well, I'll look at the voltage on channel 1 again, like we've been doing, and I will look at the current on channel 2. Okay, and so again, same idea, bit more complicated, because I've got all three of them acting together. All right, well, I guess I've got voltage as a function of time here. Then I guess I would have the voltage from my inductor. Then I guess I'd have my voltage from my capacitor. And then I would have my voltage from my resistor. That'd be 0, right? That would be adding up around the loop. But what I want to do is take a little bit of advantage of a couple things you already know. First of all, the phase relationship between the current and the voltage. And the other part here is just the series. And this is why we do series first, and for this class, this is why we only do series. What would you say, since they're in series, about the current in each of these? It's the same. They're in series. Fair enough? Okay. So let's do something like this. Let's change our notation just slightly. It was nice to talk about the voltage changing with time when I was kind of explaining what was going on. But it might be more helpful to just say there's going to be some current set up. And as the current gets set up through here, it's going to change with time. Now, the reason I want that is I need some kind of relationship between my current and my voltage. Okay? So if I was making a graph of current, so blue for current, it would look like this now. If I was drawing a phasor for the current, I guess it would start here and swing around, right? A sine function. Okay? So, question, does that look like that? There's my sine function. There's my stick, starting at angle 0, like a sine function, height of 0, spinning around. All right. Now, let's add these together. All right. And I guess it would look something to this effect. Let me just put all of this on the other side of the equation. And I might not even pay too much attention yet anyways to the sign. So let me just put them all together. I know they're all negative on that side of the equation here. But these are all really going to be negative numbers. Isn't that minus L, di, dt, you know. But let's look at the voltage, say, from the inductor. What did we learn earlier on here? Well, I guess we really learned that the voltage from the inductor would be XL times the maximum current in the circuit, right? times what kind of function here? What did we say about the inductor? Does the voltage on the inductor happen the same time as the current? No. Remember, Eli, which came first here? Yeah, E. So if I were to put the inductor voltage on this graph, wouldn't it be something like this? Isn't this the voltage of the inductor? Voltage comes first. Isn't that a cosine function? Right? And so I would have cosine omega t. You see, this is why I was saying earlier on, we want to learn phasors here because when I go to add up the voltages, I've got three different elements to add up: the inductor, the capacitor, and the resistor. But is their voltage in the same phase? No, they're out of phase. So I've got to add up three different sine functions. And this would have been hard, except I have phasors to help me out. Right? So this is my first one. This is my voltage from my inductor. What would it look like in my phasor diagram? It would be a stick like that, right? It would be a voltage of my inductor, 90 degrees ahead of my current. Right? I'd get voltage first, then current. How about my capacitor? What would it look like? Yeah, I guess it would look like the reactance for the capacitance times the maximum current. That would give me my maximum voltage. Okay, times what? Yeah, it'd be a negative cosine. Maybe I'll do that one in green. And so this green one is the voltage I get from my capacitor. And so I will put a, I'll just change the plus to a negative cosine omega t. And then finally, what's the voltage on the resistor? Well, that hopefully is the easiest one. Voltage on the resistor is just the resistance times the current times sine omega t. Okay. In this picture, it would look like, and I'll put that one in red, this. And so here's the voltage from the resistor. Now you can see this is getting pretty ugly looking here with all these voltages, right? So I'm hoping it'll look a lot easier when I do my phasors. And it will. I've got three trig functions to add together, right? 4 to visualize, 3 to add together. I got to add the voltages. I'm not going to add current to voltage. That doesn't make any sense. But I got to add the voltage of the inductor, the voltage of the capacitor, and the voltage of the resistor. And I want to add those 3 together. And that's what this is saying. And like I said, I would have to either do some trig identities to add sines and cosines together, or I can come over here and put it in my phasor diagram. So we got the inductor. What would the voltage on the capacitor look like? That would be a little stick going down, so there's the voltage on the capacitor. What would the voltage on the resistor look like? It would be a little stick like that. Maybe I'll give it a little longer, like that. And so there's the voltages on the resistor. Let me jump back to your textbook. Then this next section, which I think is section 5, what your author calls the RCL circuit, he says this, look, if your current has this pattern, and so there it is in purple, you would have the voltage from the resistor, you would have the voltage from the inductor, you would have the voltage from the capacitor. You would have those three trig functions to add together. I put them on top of each other. He separated them out. Each of them I think has their advantage. That looks less cluttered, but it's harder to see the time scale. But you want to add those three together. Like I said, one option is to do your trig identities. We're going to avoid that so that we can introduce you to some mathematics of adding phasors together, and that's what this little picture is, right? Here is the stick for the current, so we'll give it a different color, but he puts the voltages all in the same color. Here's the stick for the resistor, here's the stick for the capacitor, here's the stick for the inductor. Imagine all three of them spinning. The good thing is they spin together as a group. So how do you add them together? Freeze frame, add the vectors together, that's going to give you the magnitude, right? And so imagine these sticks spinning and then add them, and so this picture will help a lot right there. The sum of all of these is simply a picture. I have no other color options here. Maybe I'll go back to black here. But if you put these two together, then you've got VL minus VC. That's how high it goes. So I've drawn VL bigger than VC, like your author did. And then I've got VR out to here. And so there is the total voltage. A vector sum. And they're at right angles, so it's Pythagorean's theorem. How great is that? It's going to be easy to add together. Yeah.
I'm confused about the sign when we put in the Vmaxes for the capacitor and the inductor. Should the inductor be negative, capacitor positive, or positive?
How's that?
So then on the bottom, the line below it, is that positive, negative, positive? Or was it?
Well, then this one had a negative inside of it, so the negative here canceled with the negative there. I just switched the time scales to make it positive. This one already had a positive, so that's one with that negative. Oh, that kind of messes up that one. Maybe that wasn't a good answer. Maybe I
The absolute value for this one, that negative doesn't.
I'm looking for a good math answer. What am I missing here?
Depends if you're measuring the voltage of it's being consumed or the voltage being produced. It would be opposite in sign.
Yeah, but I guess I want to be consistent here. This should have been a minus L di dt. And this should have been a C over, or Q over C. And this should be a minus IR. Okay, so there's my answer. When I move it to this side, it's a plus IR, right? And when I move it to this side, it is a minus the charge. And when this minus moves over there, it becomes a plus. That was, okay, yeah. I should have wrote it out in detail, yeah. Okay, all right. But again, part of this, like I said, is really setting you up, not so much for this semester, but next semesters, and where you say, hey, what are phasors? They do become a powerful math tool for adding trig functions together. And you will see them. They are used a lot. And like I said, this is one example. We do it in optics. So those of you who had me for optics last semester, those of you who will have me for optics next time, we use our phasors a lot. And so this is our phasor diagram. Now, and here was that advantage. What I'm going to say here, I am going to add these together very simply in my head to get the answer. Wow. That plus that plus that, looking at this picture, will give me the answer. Ready? And again, there's really no other way to do this than to say, do you see it in your head? It's very pictorial. First of all, 3 sticks added together, spinning, are going to result in 1 stick spinning. Fair enough? What rate is it spinning? All right, sine omega t. Yay! There's the first part of adding those 3. I just know that's the kind of the neat thing about the phasors. All of them spinning at the same speed, going to add up together to the resulting spinning at the same speed. Sweet. Oh, I should have left this open a little bit. Because even you can see here, that stick that's spinning has a phase that is different than 0 from the current. So plus a phase. And how would I get that phase? Yeah, the tangent of that phase would be what? It would be this height, which is VL minus VC over VR. And that is current times the reactance, current times the reactance, current times the resistance. And so all the current cancels off. And so there's the first part of this is the phase. The phase between the current and the voltage is really dependent upon all 3 factors. How much inductance do you have? How much capacitance do you have? How much resistance do you have? We'll look up the circuit here in a second, but there's the phase. Yeah?
Do you want us to calculate the
What do you mean by calculate?
the real and imaginary going phasors back and forth?
Oh, notice I didn't say anything about imaginary numbers. You could do all this using imaginary numbers.
Right.
And if you want to, that's fine.
We're doing that in circuits.
Okay.
We just use the calculator to go back and forth between, instead of taking the tangent,
Okay.
calculate it. So, do you want us to show the work for that?
No. I mean, if you're doing that in circuits, that's fine. I'll just say that this book nor I will do imaginary numbers. That's one more step of mathematics. I love it. It makes the equations a little simpler, but it also pulls you away from the physics a lot, and you may not see why we have these relationships. So as you'll see, your author just no imaginary numbers. With the idea to, save that for later on. Anyways, but I want you to see again that see how easy it was for me to add those together. I'm not done. I got a magnitude out here. But again, I bet you can get the magnitude. How are you going to get the magnitude?